Hello, students. Today, we're embarking on an exciting journey to explore the chemistry of phenols, especially how we prepare them. Imagine phenol, also called carbolic acid, as a molecule that's been known for over 2 centuries since it was first extracted from coal tar. Although we now produce it industrially through synthetic routes, understanding the basic laboratory preparations helps us grasp the foundational organic reactions. One common starting material is chlorobenzene, which includes a benzene ring bonded to a chlorine atom. This molecule is quite stable, so replacing that chlorine with a hydroxyl-OH- group to produce phenol needs special conditions. As we look at the figure on your screen, notice this conversion involves treating chlorobenzene with sodium hydroxide or NaOH under extreme conditions. That means heating at 623 Kelvin, which is about 350 degrees Celsius, and applying a very high pressure of around 300 atmospheres. The reaction is a nucleophilic aromatic substitution where the hydroxyl group replaces chlorine, creating sodium phenoxide initially. This intermediate is then acidified using hydrochloric acid, or HCl, protonating the sodium phenoxide to give us phenol. We'll break down each of these steps carefully over the next few slides, so stay curious and keep imagining the molecules transforming right in front of your eyes. Let's dive deeper into the preparation of phenols from haloarenes, especially chlorobenzene. Look closely at the figure displayed, which walks us through this fascinating reaction. Step 1 begins with chlorobenzene, a stable aromatic compound with a chlorine atom attached to the benzene ring. To swap this chlorine for a hydroxyl group, chlorobenzene is fused with sodium hydroxide, or sodium hydroxide, under severe conditions, specifically at 623 Kelvin, which is very hot, and about 300 atmospheres of pressure. Under these conditions, the hydroxide ion from sodium hydroxide acts as a nucleophile and attacks the aromatic ring, displacing the chlorine atom in a nucleophilic aromatic substitution reaction. This produces sodium phenoxide, the benzene ring bearing an O-Na+ group. Next comes acidification. Treating sodium phenoxide with hydrochloric acid, or HCl, protonates the oxygen, converting the phenoxide ion into phenol with an HOH group attached to the benzene ring. The overall reaction can be summarized simply. C6H5CCl plus NaOH gives C6H5ONa plus HCl, which upon acidification further yields C6H5OH, phenol, and sodium chloride. This process showcases the clever ways chemists overcome the stable nature of aromatic compounds to modify their functional groups. Do you see the power of conditions in shifting the course of a reaction? Keep these ideas in mind as we continue. Moving on, let's discuss another elegant method for preparing phenol, starting from benzene through its sulfonation. On the screen, see the detailed reaction scheme illustrating this pathway. First, benzene, a 6-carbon aromatic ring, reacts with oleum, which is essentially sulfur trioxide dissolved in concentrated sulfuric acid. This reaction is known as sulfonation and adds a sulfonic acid group, SO3H, to the benzene ring, forming benzene sulfonic acid. The benzene sulfonic acid is then treated with molten sodium hydroxide. The strong base helps replace this sulfonic acid group with an O-Na+ group, creating sodium phenoxide. Finally, acidifying sodium phenoxide with dilute acid like HCl returns the hydroxyl group to the benzene ring, giving us phenol. Thus, we transform benzene through a fascinating sequence involving electrophilic aromatic substitution, followed by nucleophilic substitution and acidification. This method is industrially and academically important as it allows us to convert hydrocarbons into useful phenol compounds. Are you imagining the sulfonic group stepping off and making way for hydroxyl in this transformation? It's chemistry at work, showing the power of functional group interchanges. Next up is a method that involves the creation and transformation of diazonium salts, which are fascinating intermediates in organic chemistry. Let's focus on the molecule aniline, which is a benzene ring attached to an amino group, NH2. At very low temperatures, between 273 and 278 Kelvin, we add sodium nitrite, NaNO2, and hydrochloric acid, HCl, to aniline. This forms benzene diazonium chloride, where the amino group is converted into a diazonium group, which is N2+. The salt is positively charged on the nitrogen and paired with a chloride ion. The equation to remember is C6H5NH2 plus NaNO2 plus 2HCl gives C6H5N2 plus Cl minus plus sodium chloride and water. This process is called diazotization. Then, we gently warm this diazonium salt with water or dilute acid. The diazonium group is replaced by a hydroxyl group, forming phenol. You'll also notice the formation of nitrogen gas, N2, which escapes as bubbles. This two-step pathway, from aromatic amines to diazonium salts, and then hydrolysis to phenols, is an important synthetic route. Now imagine the nitrogen gas bubbling out as the molecules rearrange. It's like a microscopic fireworks display indicating the reaction's progress. Now let's look at an industrial-scale preparation of phenol, known as the cumene process. It's an elegant example of how chemical industries convert simple hydrocarbons into valuable products. As you see in the diagram, cumene, which is isopropyl benzene, reacts with oxygen from the air to form cumene hydroperoxide. Cumene structure consists of a benzene ring attached to an isopropyl group, that is, a carbon bonded to two methyl groups, CH3, and the ring. When cumene reacts with oxygen, O2, the oxygen adds to the side chain, specifically forming a hydroperoxide group, OOH, attached to the benzoylic carbon. This cumene hydroperoxide is then treated with dilute acid, which causes the hydroperoxide to cleave. This cleavage simultaneously produces two compounds, phenol, the benzene ring now bearing a hydroxyl group -OH, and acetone, a smaller molecule with formula CH, 3COCH3. It's fascinating because we get not just phenol, but also acetone, an important solvent and industrial chemical. Imagine a factory producing barrels of both from a single starting material. That's efficiency and smart chemistry combined. Let's explore how physical properties such as boiling points vary in alcohols and phenols, and how molecular interactions influence these properties. Take a look at the figure on your screen. On the left side, we see a linear chain of ether molecules connected by hydrogen bonds, depicted by dotted pink lines. These weak but significant bonds happen when a hydrogen atom connected to oxygen interacts with another oxygen atom. Moving to the right side, the image shows a cyclic structure formed by two ether molecules linked through hydrogen bonds, making an even more stable network. Alcohols and phenols have hydroxyl-OH groups that participate in similar hydrogen bonding, giving them higher boiling points than ethers or hydrocarbons of comparable molecular masses. For example, ethanol boils at 351 Kelvin, much higher than methoxymethane and ether at 248 Kelvin, despite both having a molecular mass of 46. Now, think about branching too. When alcohols have branching in their carbon chains, the surface area reduces, weakening van der Waals forces and lowering boiling points. So, Primary alcohols often have higher boiling points than their branched tertiary counterparts. Hydrogen bonding acts like tiny molecular handshakes, holding molecules together strongly, requiring more heat to separate them. This physical property directly impacts how substances behave, from boiling to dissolving, and is crucial in fields from cooking to pharmaceuticals. On this slide, we'll compare three compounds with similar molecular masses to understand how their structures affect their boiling points. First, ethanol, with formula C2H5OH, has a hydroxyl group capable of forming hydrogen bonds. This interaction creates strong attractions between molecules, leading to a boiling point of 351 Kelvin. Methoxymethane, also known as an ether with formula CH3OCH3, can't form strong hydrogen bonds with itself because it lacks hydroxyl hydrogens, though it has dipole-dipole interactions due to the oxygen atom. Therefore, it boils at a significantly lower temperature of 248 Kelvin. Finally, propane, a hydrocarbon alkane with formula C3H8, has only weak London dispersion forces holding its molecules together. This accounts for its lowest boiling point of 231 Kelvin. Even though all three compounds have nearly the same molecular mass, their intermolecular forces differ dramatically, illustrating why functional groups and bonding types are crucial in determining physical properties. It's like comparing friendships. Some connections are stronger and harder to break. Here we examine why alcohols and phenols dissolve well in water, which is key to understanding their behavior in biological systems and industrial applications. On the screen, notice ethanol's structure with its two carbons and an OH group. The oxygen has lone pairs of electrons, making it an excellent partner for forming hydrogen bonds. Water molecules, consisting of an oxygen bonded to two hydrogens, are also highly polar and engage in hydrogen bonding. The image shows ethanol-hydrogen bonding with three water molecules, represented with dotted pink lines. This ability to form strong intermolecular hydrogen bonds with water molecules explains the solubility of alcohols and phenols. However, as the hydrocarbon portion of the molecule gets larger, think long carbon chains or big aromatic rings, the molecule becomes more hydrophobic, reducing solubility. Understanding these molecular interactions helps us explain phenomena like why small alcohols like methanol or ethanol mix well with water, while long-chain alcohols behave like oils. Think of the hydroxyl group as the friendly handshake enabling ethanol to mingle effortlessly with water molecules. Let's put our understanding to the test with a real example from your textbook. Example 7.3. The question asks us to arrange sets of compounds in order of increasing boiling points. Starting with part A, all compounds are alcohols, which means they have OH groups that can form hydrogen bonds, significantly raising boiling points compared to nonpolar molecules. Factors such as molecular size and branching come into play too. Larger alkanols tend to boil at higher temperatures because of increased van der Waals forces. The correct order is methanol, ethanol, propan-1-ol, butan-2-ol, butan-1-ol, and pentan-1-ol. Notice that butan-2-ol, a branched molecule, has a slightly lower boiling point than butan-1-ol due to reduced surface area. In part B, we compare different functional groups. N-butane is a nonpolar hydrocarbon with weak intermolecular forces, so it has the lowest boiling point. Ethoxyethane, an ether, has dipole interactions but no hydrogen bonding, giving it a higher boiling point. Pentanol, as an aldehyde, has stronger polar interactions, so it boils higher. Lastly, pentan-1-ol, with hydrogen bonding, comes out highest. By considering these intermolecular forces, You can predict boiling trends confidently. Now get ready for questions that will spark your own thinking. Let's explore how alcohols act as nucleophiles in the formation of esters, an important class of organic compounds. The image here illustrates the acid-catalyzed esterification mechanism. In step 1, an alcohol molecule with the general structure ROH has its oxygen's lone pair ready for action. A positively charged carbon, often part of a carbocation or activated species, is electrophilic and eager to bond. The oxygen atom in the hydroxyl group attacks this electrophilic carbon, forming a new bond and creating a transition intermediate, which looks like RHOC+. This step is essential as the nucleophilic oxygen forms a connection with carbon, changing the molecule's structure. Next, the intermediate loses a proton H+, stabilizing into an ester, where the oxygen links an alkyl group R to a carbonyl or similar functional group. This acid-catalyzed reaction is common in organic synthesis in nature, contributing to the creation of fats, oils, and fragrances. Think of it like dance partners joining hands under the spotlight of an acid catalyst, forming a beautiful new compound. Alcohols can act not only as nucleophiles, but also as electrophiles when protonated, making the hydroxyl group a better leaving group. This slide explains how this happens, especially in reactions forming alkyl halides. Initially, the hydroxyl group in an alcohol grabs a proton, H+, from an acid, transforming into a positively charged oxonium ion, RCH2OH2+. This protonation is crucial because the water molecule can leave more easily than a hydroxide ion. Next, a nucleophile, such as the bromide ion, Br-, attacks the positively charged carbon attached to protonated hydroxyl, leading to substitution. The water molecule leaves, generating an alkyl bromide, RCH2Br, and water as a byproduct. This nucleophilic substitution is a vital reaction in organic chemistry, especially in the preparation of alkyl halides from alcohols. Just picture the protonation as activating the alcohol, turning a poor leaving group into a great one, letting the reaction flow smoothly. It's like unlocking a door so a new guest, the bromide ion, can enter. Alcohols and phenols, though often considered neutral, exhibit acidic behavior that we can observe through their reactions with active metals and bases. When an alcohol, ROH, reacts with sodium metal, Na, as shown in the first reaction, the acidic hydrogen on the hydroxyl group is replaced, producing sodium alkoxide, RONA, and hydrogen gas, H2. You can imagine bubbles of hydrogen escaping as the reaction proceeds. Similarly, phenols, which have the hydroxyl group directly attached to an aromatic benzene ring, also react with sodium to produce sodium phenoxide and hydrogen gas. Interestingly, phenols also react with sodium hydroxide or NaOH, a strong base, to form sodium phenoxide and water, something regular alcohols cannot do as readily. This indicates that phenols are more acidic than alcohols. This acidity is essentially about the tendency to donate a proton, H+, from the hydroxyl group, revealing that phenols are Brunstad acids. Think of the hydroxyl hydrogen as the acidic proton, willing to be shared or taken by strong bases or metals. These reactions are foundational to many synthesis pathways and the understanding of acidity in organic compounds. Continuing our journey through the chemistry of alcohols and phenols, let's frame their acidity within the Brunstad-Lowry acid-base theory. The diagram before you beautifully illustrates this fundamental concept. Here, B represents a base, a molecule or ion capable of accepting a proton, indicated by the colon showing a lone electron pair. The acid, HOR, has the all-important proton bonded to oxygen. When the base approaches, its electron pair attacks the proton on the acid. This is illustrated by a curved arrow directing from the base's lone pair to the hydrogen. Simultaneously, another curved arrow moves electrons from the HO bond to oxygen, showing bond breakage and proton loss. As a result, the base becomes its conjugate acid BH, having gained a proton. The acid loses its proton and becomes the conjugate base O-R, possessing a lone pair of electrons on oxygen. This proton exchange reveals the reversible nature of acid-base reactions and the dynamic electron movements underlying all chemistry. Visualize this proton donation like a handshake transfer from an acid to a base, maintaining chemical balance and preparing molecules for the next step in their transformations. Understanding acidity strength requires us to look at the structure of alcohols more closely. Alcohols can be primary, secondary, or tertiary based on how many alkyl groups, or carbon-containing groups, are bonded to the carbon atom connected to the hydroxyl-OH- group. See the structures displayed. Primary alcohol has one alkyl group and two hydrogens. Secondary has two alkyl groups and one hydrogen. And tertiary has three alkyl groups and no hydrogens. Electron-releasing alkyl groups increase electron density around the oxygen atom, reducing the polarity of the OH bond. This makes it harder for the proton to dissociate, thereby decreasing acidity. Hence, acidity decreases in the order. Primary alcohols are more acidic than secondary, which are more acidic than tertiary. This is because tertiary alkyl groups donate more electron density, stabilizing the bond and preventing proton release. The accompanying table summarizes this classification and the corresponding structural differences. By appreciating this, you can predict and explain chemical behaviors based on simple molecular architecture, a true power of chemistry. Phenols are fascinating because their acidity is quite unlike that of alcohols. The key lies in resonance stabilization. Look closely at the first image displaying the resonance structures of phenol. The phenol molecule's oxygen atoms can share and delocalize their lone pair electrons with the benzene ring's pi system. This delocalization spreads the negative charge over multiple atoms in the phenoxide ion formed after deprotonation, stabilizing it substantially. The figure beautifully shows anti-clockwise movement of pi electrons and lone pairs, shifting positive and negative charges around the ring. This stabilization favors phenol's loss of a proton, making it more acidic than typical alcohols. The table lists pKa values for various phenols and ethanol. Notice how electron-withdrawing nitro groups, NO2, at ortho and para positions dramatically lower pKa, making phenols far more acidic. Conversely, electron-donating methyl groups slightly raise pKa, reducing acidity. This interplay of resonance and substituents is like a tug-of-war over electron density, determining how easily the proton leaves. Such understanding is pivotal for chemists designing molecules with specific acid-base properties. Let's close our lecture today by applying what we've learned through example 7.4, which challenges us to arrange several compounds in order of increasing acid strength. The list includes propan-1-ol, 4-methylphenol, phenol itself, 3-nitrophenol, 3,5-dinitrophenol, and 2,4,6-trinitrophenol. Remember, the acidity is impacted largely by substituents attached to the phenol ring. Propan-1-ol, being a simple alcohol, is the weakest acid here. The methyl group in 4-methylphenol donates electrons, further decreasing acidity compared to phenol. Phenol is a baseline for us. Introducing nitro groups, which are strongly electron withdrawing, increases acidity. As these groups appear more and in positions ortho or para to the hydroxyl group, in 3-nitrophenol, 3,5-dinitrophenol, and especially 2.4.6 trinitrophenol, acidity rises considerably. Hence, the order from weakest to strongest acid is propan 1, O less than 4-methylphenol, less than phenol, less than 3, nitrophenol, less than 3, 5.